Welcome to ECE CS 552 Introductory Lecture. This course is an introduction to computer architecture. Computer architecture is really the art and science of interfacing software or algorithms to hardware that executes those algorithms. We can typically think of computer architecture as being defined at three different levels. The most straightforward and clear to understand level is what's called the instruction set architecture. This is a concept that was invented by IBM in the IBM 360 line of computers in the early 1960s. And the idea of an instruction set architecture is to provide a clear, well-defined interface that describes the attributes of the computing system that are needed by the programmer to use the computing system in a way that is both clear, well-defined, and persistent, meaning that even as the hardware changes underneath that interface, existing software will continue to run. This was a novel concept at the time. It's something we take for granted today. We assume that even if we buy a new computer, a new PC, or a new laptop, all of our old programs will continue to run. This was not true until the introduction of the IBM 360 line of computers in the 1960s. Even today, you can still buy a compatible system from IBM that will run program binaries that were written in 1964, and they will work flawlessly. Two other layers that dig a little bit deeper behind the concept of computer architecture are the machine organization or microarchitecture layer. This is really the organization of the hardware itself. How many units will be there to execute arithmetic and logic instructions? These are called ALUs. What kinds of buses are used to connect pieces of the system to each other? What kinds of memories do we have in the system? How large are they? How are they addressed? What kinds of cache memories do we have? Again, how are those organized and indexed? So these are sort of the high-level, somewhat abstract description of the hardware itself. Digging even deeper than that is the machine implementation layer, or the realization layer, where we actually have now gates, cells, transistors, wires that are used as building blocks to implement all of the blocks that are described in the machine organization level description of the machine. Let's talk a little bit about 552 in the context of the other courses that you might have taken and other courses that you might want to take going forward. Prerequisites for the course are 252 and 352, where you learn about digital logic, you learn about gates, you learn about memory and how it's organized. Also 354, where you learn about high-level languages and how they are mapped or compiled down to the machine language interface, again, which is specified by the instruction set architecture. This course, 552, really puts these concepts together. We teach you how to implement the logic that provides that instruction set architecture interface. You will have to design data path and control logic in this course. We're going to try to remove all of the magic there, so there's no more mystery around what has to happen to make this all work together. And you'll learn about some of the tools that we use. The most important tool is really a concept called abstraction that's used to manage the tremendous complexity that is hidden inside these computing systems. If you really enjoy this course and find that you like it, we have several follow-on courses that explore many more trade-offs and concepts in this space. We have ECE 752 and ECE 757, which are focused on high-performance single processor design in 752. And 757, we focus on high-performance multiprocessor systems. And then more on the circuit and logic design side, we have ECE 555 and 755, which are focused on VLSI design. Why would you want to take a course like 552? Well, one of the primary reasons would be to become a computer designer. Alumni of this class have helped design your computer. There are virtually no existing computer systems out there that have not been touched by at least one Wisconsin alumni in the process of them being designed. Graduates of this course, graduates of this program go on to all of the major computer companies to help design the next generation of processors and computing systems. You might also just want to take this course because you want to learn what is under the hood, even if you have no intention of ever becoming a computer designer. Many people just have an innate curiosity that helps them better understand what is happening when things don't work the way they expect them to, or things even break. Having this knowledge will also help you become a better programmer, write better code applications and system software. If these are your part of your future career plans, then the concepts you will learn in this course will be very, very useful and valuable in that career. And finally, I think because the design of these systems is intellectually fascinating, you could easily make the argument that the most complex, highly integrated, engineered, or man-made devices are in fact the CPUs that we design and ship today. As mentioned, one of the key tools that we use in designing these systems is the concept of abstraction. This is something that helps us manage complexity. And the key thing here is to provide interfaces between layers of abstraction. And the interfaces are there to specify what to do while hiding the details of how that's done. So if you look at this stacked chart here on the right side of the slide, this kind of illustrates several of the layers that exist in an existing computer system. At the very top, we have application programs that you're all familiar with. You've all used a web browser or you've all used an Excel spreadsheet. Those application programs are what's visible to the end user. They provide all of the logic and all of the user interface widgets and so on that you as the end user interact with. These application programs then communicate through the operating system, shown on the right here, to invoke system-level services like opening files, closing files, establishing a connection over a network link, and so on. The application programs themselves are typically written in a high-level language, such as the Java language that you learned in CS 302. These programs are then compiled into this machine language representation that you learned about in CS 354. If you're curious about how that seemingly magical transformation from a high-level language program to a machine language level program occurs, I would encourage you to consider taking the compiler course CS 536 as an elective. Below that machine language layer then is digital logic. You learned about digital logic and how to build both combinational logic as well as sequential logic in 352. Below that, of course, we have electronic circuits. Depending on your background, you may have taken ECE 340, where you saw how some of these structures and circuits are built. Even further below that are semiconductor devices. And if you're a double E major or a computer engineer, you've seen some of those concepts as well. Now, the goal of this course will be to try to remove what seems like magic in this whole process of taking a high-level application program and actually having it move current around essentially in circuits from node to node, and somehow have that moving of current around or moving of charge around as current to actually implement the semantics of the program. And basically the scope of this course is to bridge what you learned, the concepts you learned in 352 and the concepts you learned in 354, and to show how the two meet and how we can actually build, using the digital logic building blocks from 352, an entire system that is now able to execute programs that are specified in this machine language. Fundamentally, computer architecture as a practice is an exercise in engineering trade-off analysis. What you're tasked to do as a computer architect or designer of a processor is to find the fastest or cheapest or most power-efficient solution for a particular task. Now, the metrics that you care about will vary depending on the requirements that you're given. Sometimes you really want the highest performing system. Sometimes you want the least expensive. Sometimes you want the one that consumes the least power. The problem is there are hundreds of variables that you can vary in this problem space, and so optimizing them becomes extremely difficult. Not only are there hundreds of variables, but the variables are changing in terms of their relative effects, and they're changing at non-uniform rates, and there are inflection points because of the technology advancements that are there that pretty much lead you to the conclusion that there's only one guarantee for a computer architect. The right answer that you come up with today will probably be wrong tomorrow. And as a computer architect, we really have to cope with sort of two very high-level effects that are affecting the technology, because the technology push is essentially causing the devices that we use to build systems to have different attributes and different characteristics over time and changing at a very rapid rate. At the same time, there's application pull, where clever programmers, clever application developers are constantly coming up with new ways to use the technology. So let's talk first about technology push. If you think about these two intervals from 1776, when the United States was declared independence from Great Britain, to 1999, which is 224 years, versus 2000 to 2001, just a short 2-year gap over a decade ago. What do these two intervals have in common? Well, the answer is there's been equal progress in processor speed in those two time intervals. And the reason for that is that we've experienced and have been experiencing for many decades now exponential growth in processor speed. Where this growth is coming from is a concept called Moore's Law. This was a law that one of the early pioneers in our industry, Gordon Moore, proposed only a few years after the concept of an integrated circuit, which is essentially a chip that has more than one device integrated onto it, was invented in the late 1950s. So in the early 1960s, Gordon Moore basically observed that as industry was working on these integrated circuits, the number of devices that could fit on a chip was doubling about every 18 to 24 months. And this is a prediction that he made that has surprisingly held true now for 5 decades. And really, one of the jobs that a computer architect has is to try to turn the additional resources, the additional devices that we can now afford per chip in every process generation that comes along every 1.5 to 2 years. We want to try to turn these devices or convert them into better performance or speed, lower power, or better functionality, or some other desirable attribute that customers will want to buy. So let's back up a little bit and look at some history in our space. So if you go all the way back to 1939, the first digital computer was built by a fellow called John Atanasoff. He was working in Iowa. He actually had a PhD in physics from Wisconsin from 1930. So that was conceived as the first digital computer. In 1947, the first transistor was invented. So until the transistor was invented, computers were implemented using in some cases, mechanical devices like gears and levers. In other cases, tubes, similar to the tubes that you used to see in old school televisions. But transistors were really the key invention that enabled much greater reliability as well as much higher levels of integration, meaning we could have many millions of transistors making up a single system, and because they were so reliable, we could still actually get the computer to stay up and running long enough to actually perform some useful computation. About a decade later, in the late 1950s, the integrated circuit was invented, and one of the two inventors of that was Jack Kilby. He was at Texas Instruments at the time. He was actually granted the year 2000 Nobel Prize for this invention. He also has a degree from University of Wisconsin, another famous alumni of our program here. In the 1970s, the concept of the microprocessor was invented. So the first microprocessor was built by Intel in the 1970s, followed by the Intel 4004 and the Intel 8086. Now, what is a microprocessor? A microprocessor is simply a single chip that now has enough resources on it that we can implement the entire processor, the data path and the control for the processor on a single chip. The initial ones were, of course, very small and modest. The 4004 had 2,300 transistors. A few years later, we had 29,000 transistors, and then another decade later, in the 8486, we had 1 million transistors. So you can see this exponential growth taking place as you look at these device counts. More recently, in the mid-90s, the Intel Pentium Pro came out. That was 5.5 million transistors. And then about a decade ago, we crossed the threshold over 1 billion transistors with the Intel Montecito design. So if we think about this performance growth relative to other industries, it's actually pretty amazing. So these are some numbers that John Crawford, who's an Intel fellow, put together a while ago in a talk. But if you think about performance growth in the computer industry from, say, 1982 to 1996, and you assume that it's been doubling every 18 months, which is a metric or a result that actually matches reality, cumulatively that's an 800x improvement in performance in computing systems. So if we made the same kinds of improvements in automobiles, they would travel at 44,000 miles per hour and get 16,000 miles per gallon. Air travel, we could travel across the whole country in 22 seconds at Mach 800, or In terms of wheat yields, for those of you who might have a better sense of how significant this result is, I don't really have a farming background, so this is a bit of a mystery to me, but we would be getting 80,000 bushels per acre, which I'm told is a pretty astounding number. Or if we look back a little bit further, the doubling rate slows down a little bit because the progress was a little bit slower earlier on. But still, from 1971 to 1996, there was a 9,000x improvement in computing performance. And you can then see how these three other metrics become rather ridiculous. And then these numbers, I'm putting these numbers up here just to really give you a sense for the amazing advances that have taken place in the last several decades. So the other interesting thing about this technology push is that the technology doesn't advance at a consistent rate, even though most of the components are built using the same technology, uh, these integrated circuits. Because of the characteristics of these different circuits, we end up with very different improvement rates. So for example, DRAM, which is used to implement your main memory, has been focused on increasing capacity. And so the capacity has been increasing at a rate of 60% per year. But the latency to access that memory has really only been increasing at a pretty marginal rate of 10% per year. If at the same time your processors are actually increasing their frequency at a much higher rate, the gap between the main memory and your processor in terms of the mismatch in their operating rates, their operating frequencies, keeps growing. So this causes challenges and headaches for computer architects. And then there are also inflection points where you reach a certain point where, for example, you have enough devices to implement a whole microprocessor, like we talked about in the early 1970s with the early Intel microprocessors, or much more recently, we actually have enough devices that we can build many processors on a single die, a multi-core or many-core system. This happened a little over 10 years ago. Some of the current issues that are causing inflection points in the way we design systems are specifically power consumption has become much more important these days, especially with the advent of actually very high performance computing systems that are portable, that are embedded in smartphones, for example. Reliability and variability are also becoming bigger and bigger problems as the device technology that we use, essentially the Moore's law scaling that we talked about, is coming from making the devices smaller and smaller and smaller by a factor of 2 with every process generation. The smaller we make them, the harder it is to make them reliable so that they last a long time, so they don't have intermittent and permanent failures. And also variability, which means every device is no longer the same. We fabricate 1 million or 1 billion devices. Every single one has different operating characteristics, so it becomes very difficult for us to make guarantees about how fast we can run them, what temperatures we can run them at, what voltages we can run them at, and so on. So these are all issues that architects today are having to deal with in addition to the problem of performance. On the flip side of the technology push, we also have an application pull, and you can kind of think of this as a corollary to Moore's law. So rather than thinking about it as the number of devices doubling, you can think about it as the cost being halved every 2 years, because the cost to fabricate a single chip remains roughly constant, but the functionality that you can provide with that single chip is now going to be roughly twice as good. So thinking of it from the perspective of cost, you're getting the same functionality for a lot less money over time. So what this means is that computers become cost effective for increasingly seemingly trivial kinds of applications. So for example, initially in the 1950s, or going back all the way to the 1940s and World War II, computers were only cost effective for applications like national security. So essentially, if you were a wealthy first world nation, you could afford a computer, and that was it. As we went into the 50s and the 60s, it became possible for large businesses, enterprises, to afford computers for purposes like banking and payroll processing. As we got into the 70s and 80s, it became departmental. You could have a mini computer that you could share with the 20 people in your department for various tasks, including things like computer-aided design. And then in the 80s and into the 90s, personal computers became pervasive. So every worker and even every person at home could have their own computer. They became affordable at that level. And then going forward, it's really an open question. What are the things that we can afford going forward? I mean, these days, of course, everyone has a computer in their pocket. in the form of their smartphone. Not everyone, but there are a billion or more of those out there today for a global population of only 7 billion. And moving forward, we see things like Fitbits and other kinds of personal health and fitness devices or wearable computers that are becoming decreasingly expensive, so more and more affordable for a larger and larger fraction of the population, and performing applications that we never would have conceived would be feasible on a computing system, 10, 20 years ago because of cost. So as we look into the future, what are the kinds of applications that you might think will become cost-effective on computing systems? There are certain things that even a short while ago were very expensive and were not cost-effective, like telepresence, attending meetings without actually traveling, virtual reality. If you've been following the Oculus Rift releases that have been coming out, some pretty amazing stuff is becoming possible today. Mobile applications, again, things that 5, 6 years ago seemed impossible, are now something that we consider as very everyday kinds of applications. Going forward, some of the things that people are looking at actively are in the space of what's called the Internet of Things, where you actually have lots of devices that build in sensing capabilities, analysis capabilities, even actuation for robotic kinds of activities in real-world environments. But really, to a large extent, this is going to be your generation's job to figure out and define and innovate what are the new ways that we can use computing that are enabled by the fact that it's become affordable and inexpensive. Hopefully, I've motivated you that these two factors, application pull and technology push, make life for an architect very interesting. Now let's talk a little bit about this notion of abstraction, this concept that we introduced a few minutes ago that helps us manage the complexity in these extremely complex system designs. Abstraction is really, you can think of it as the difference between the interface to a particular piece of functionality and the implementation of that functionality. The interface will tell us what something does and will give us a way to invoke that functionality, but will hide the details of how it does so and leave those up to the implementation. An example of an interface is a 2-to-1 multiplexer, which is a digital logic structure that you learned about in 352. It provides a very simple interface. There are two inputs, X and Y, and a select input S. And the select input S is used to govern whether X is routed from the input to the output or Y is routed from the input to the output. We can reason about and design circuits and systems using multiplexers as a building block without knowing anything about the implementation of the multiplexer. It could be implemented with gates, which could be fast or could be slow, could be consuming a lot of power or not a lot of power or very little power. We could implement it with pass transistors. We could implement it with distributed tri-state kind of design. There are lots of different ways to implement multiplexers, but again, in the process of designing a system that uses muxes, we don't necessarily have to know anything about that implementation as long as that implementation adheres to this abstraction, to this interface that's clearly defined for this structure. So what is the big deal about using abstractions? Well, again, we have this tower of abstractions that we talked about before, where we have applications at the top, and at the bottom we have devices that are behaving according to the rules of quantum physics. In between those two things, we have many, many layers that hide the details below it. And that allows now hundreds of engineers to build a single product that implements that entire stack without having to necessarily know much at all about what happens both above and below the abstraction layer that they're operating at. If we didn't have this capability to hide the details, the complexity of this entire system would be unmanageable. There's no way that a single person could implement all of this and understand all of this complexity without hiding the details using this concept of abstraction. So let's talk a little bit about the hardware that goes into these systems. We can basically divide the hardware that is used to execute or implement the instruction set architecture, which provides now the interface between the hardware and the software in terms of a relatively small number of building blocks. So on the left here, we have the data path of the processor. So this is the combinational and sequential logic that someone has to design that will actually perform the computation that is specified by the instructions in your program. That again are the instructions belong to a particular instruction set architecture. That data path has control logic in it as well to sequence the execution of those instructions through that data path correctly. We will be spending a fair amount of time in this class looking at the details that are required to actually make this all happen and work together. You will actually be building a data path that matches this description as part of your project for the course. The data path, of course, also has to interface with memory. Then memory is used to store the state of the program that's running. We have to both read inputs from memory and write outputs out to memory. Furthermore, in any system that interfaces to the external world, we also have output and input. So input might be things like your keyboard or mouse or touch screen. Output typically would be your display screen, but it could be your speaker if it's an audio output, etc. So all of these components are part of any computer system that you would be looking at today. We can also get a basic understanding of what the hardware does in terms of what happens in time rather than in space. In time, what basically has to happen is one by one, the hardware has to fetch the current instruction from memory. Let's say, for example, it's an add instruction that's taking the contents of two registers, R2 and R3, and storing the sum in register 1. So first we have to fetch that from memory, then we have to decode that, because what we're really fetching from memory is just a bunch of binary bits, and the hardware has to figure out what those bits mean. What is the encoding of the instruction? After that, it has to then, once it knows what it needs to do, it needs to start doing it. The first step typically would be to read operands that the operation needs. So in this case, we would read the two values R2 and R3 out of the register file. Then we would actually perform the addition operation, and then we would write the result back, in this case to register 1. So this is essentially what has to happen in time to execute an instruction. Finally, once that instruction has been executed, we need to determine the next instruction. For typical instructions that aren't control or branch or jump instructions, we will simply increment the program counter, in this case by 4 because the instruction size is 4 bytes, and then we'll repeat the process. We'll fetch the next instruction from the next. We'll be spending an awful lot of time in this course in the coming weeks to talk about how to actually build the sequential and digital logic that implements the steps that were specified in the previous slide. But before we get any deeper into that, let's just talk briefly about how computer chips are built, because this is important to understand from the perspective of cost and efficiency. Computer chips are built using a complex multi-step process. They start out as silicon ingots, which are sliced into thin wafers. These wafers are then processed into patterned wafers, where the patterning on the wafers actually implements the devices, the transistors, as well as the interconnect, the metal wires that connect devices to each other. And then the patterned wafers are sliced or diced into separate die. Each of those becomes a single computer chip. We now have to test the die to make sure that they're working, because some of them will fail in the manufacturing process. So we select the good ones, we bond these into a package, then we test the packaged parts, and then finally ship these to customers to make money. This slide actually illustrates this process, going from a silicon ingot all the way to tested and packaged dies that ship to customers. One of the critical factors in designing chips and designing CPUs is design time. Time to market is very important because these design will actually be worse if it's using the existing technology from 3 years ago. Now, of course, typically the new design will also employ the new technology, so this won't be the case, but it's much more difficult and challenging to both change the design and use the newest process technology at the same time. This is one of the reasons why Intel, in about the last 10 years or so, has been employing a design philosophy called tick-tock, where they come up with a new design, but they implement the new design in the current process generation, and then a year later, roughly, they release that new design, but now mapped to the next process generation. So rather than trying to change both the design as well as the process at the same time, they stagger those, and as a result, they have essentially a new design coming out almost every year, and every other design is a new part coming out every other year, and every other one is an actual new design, and the next one is simply the talk part is just a new process for that new design. So this is an approach that has been working very, very effectively for them. So summarizing this introductory lecture for ECCS 552, Blau and Brooks, two very famous computer architects, have called this the art and science of instruction set processor design. And the reason they call it an art and a science is that there are so many variables at play in this process, and there's so much creativity required in designing new CPUs that simply calling it a science or simply calling it an engineering discipline is a bit of a misnomer. There definitely is an artistic element required in this process. One of the most important things that CPU designers need to have is a good understanding of both software and hardware, because if you don't understand how the software works, or you don't fully understand how even the lower levels of the hardware work and what the characteristics of the devices and circuits are, you will have a very hard time designing a CPU that really is optimal in any sense for that particular place and time. We also talked a little bit in this lecture about IC costs, design time, and performance. We'll be revisiting performance in subsequent lectures. IC design, circuit design, low-level circuit and logic design is not really a topic of this course. If you're interested in that space, I would encourage you to take ECE 555.